Hi friends, welcome to my channel. Let's have a look at an easy problem. Problem 653. To sum 4. Input is a binary search tree. In this video, we're going to share two treatments for this problem. The first one is based on in-order traversal of the tree plus the standard two-pointer trick. And the second treatment is a general traversal algorithm, then plus the set and check method. First, let's look at the short statement of the problem, and then we analyze the code line by line. So, given the root of a binary search tree and the target number called k, return true if there exist two elements in the binary search tree such that their sum is equal to the given target. So here are two examples. So in example 1, the return is true. For example, the node 5 and 4 add together, we get none. So similarly, 6, 3, and 2, 7. So all sum to none. So this is the true. And in example 2, the return is false because the k is 28, but the largest value of a single node is 7. So 7 plus 7 is much less than 28. So in this problem, the return is false. The constraints for this problem are the following. First, the number of nodes in the tree is in the range given by the closed interval. One end is 1, and the other is 10 to the power 4. So this tells us that the tree is not null, and the number of nodes is bounded above by 10 to the power 4. So the latter actually defines the problem set's upper bound. Secondly, the node value is bounded in absolute value by 10 to the power 4. In particular, the node value can be negative. So root is guaranteed to be a valid binary search tree. And fourthly, or lastly, the k is in between negative 10 to the power 5 to positive 10 to the power 5, both ends inclusive. So with that said, let's look at the coding. So this problem actually is rather standard. If we have solved the classic two-sum problem, actually we not only solved the two-sum problem, we used the line of ideas to solve quite a number of other problems. Here we come to this problem just for practice purpose. So here there are two treatments to present. The first one is the in-order traversal. Then for the binary search tree, the in-order traversal of the tree will give us a sorted nodes value list from small to large. Then because the resulted list is sorted, so we can use two-pointer trick. So this is method 1. So actually for this problem, if we do not take into consideration of the BST property, then we can do a general traversal. Then use the set and check method, because the set and check method does not need the array to be sorted. So with that said, let's first look at the method 1. So here let me make some annotations. So we're going to use in-order traversal. So it's treatment 1. Let's see. Treatment 1. So here we're going to use specifically the BST property. So here we're going to do in-order traversal. In order to do in-order traversal, actually we can write a hyperfunction. Let's call it in-order traversal. So for this, we're going to accept the root or a node. Then we're going to return the list corresponding to the node values in this tree. So here we can choose to write it in an iterative format or in a recursion format. But a recursion format is sort of trivial. So let's use recursion here. So if not root, so we're going to return an empty list. So this is standard. So next we are going to do recursive call. So we're going to return in order root left and plus root value, then plus in order root right. So here, because we have treated the base case if not is null node, so here we do even the root left or root right is null, so it's still valid. So this is the function, right? So once we get this hyperfunction, actually we can, if we like, we can get the array corresponding to the binary search tree, and this array, due to the in-order traversal, is sorted. So here actually we used the binary search tree property, but we would see it's in a something weak, in a weak sense, because for this problem, if we look at treatment 2, we do not need to do in-order traversal. It's not absolutely necessary. So with that said, so we are going to do two-pointer check for this array. So for this, let me first get the length of this array, so it's not also just for convenience. So then what we are going to do is to set the left and the right to be 0 and n-1 respectively. So the L points to the beginning element, R points to the end elements in the array. Then we're going to check if the sum of the corresponding elements in the array sum up to target. If so, we're going to return true. Otherwise, we return false after the for loop or while loop. So let's see, while L is less than R. Then what we're going to get is we have a sum that is array left plus array right, right? So if S equals K, so we just need to return true, so nothing more. Otherwise, if S is less than K, so the sum is smaller than K, so we want the sum to be larger, so we increment L by 1. Otherwise, so we decrement R by 1 to make it smaller. So with that done, so actually the logic is included here. So if after the while loop nothing has returned, so we're going to return false. So this part actually is nothing but the standard two-sum problem. But here only difference is that we put these numbers in the binary search tree data structure. So with that said, let's first do a special case check. Yeah, it passes the first example. Now let's look at generic case. Yeah, it passes all the generic cases. So with that done, now let's look at the second solution. So I'll copy this function signature here, and then I'll change this one to be version 1. So with that said, let's look at the second method. So here we are going to practice the binary tree traversal. So here we just regard it as a binary tree without using the binary search property. So for this, actually we can first treat a special case. So if not root, so we are going to return false, because in this case we do not have two elements at all. So then otherwise we are going to use the set and the check treatment. So let me make an annotation again. So treatment 2. So here with that edge case treated, now let's look at the set and check. So we are going to initialize the set. So we are going to record the numbers we have seen in our traversal. So if we were given a list, so we can do a for loop, but here we want to do traversal. So I'm going to initialize a stack, so called root, and then we do the traversal. So we can do any kinds of traversal we want, as long as we can traverse the whole tree, right? So then first we are going to do the pop operation to check to get the node, and then first I'm going to write the problem logic. For the problem logic, what we are going to do is to check if k minus the current node value is in SYN. If so, it means that so the one of the previous value is given here like this, then plus the current node value will sum up to k. So in this case, we're going to return true. So this is a simple case. Otherwise, no matter what, so we are going to add this node value to the SYN set, right? So together, this forms the problem logic. And then, because we need to do traversal, so we need to incorporate the traversal logic. So here, I'm going to write a format with pre-order traversal. So in this case, I'm going to first check if node right. If this is the case, we're going to append node right to the stack. Similarly, we can check node left. So we're going to append node left. So notice that here the order is important. So here for this one, if we speak of a pre-order traversal, we first check the right and then check the left. So this traversal will give us a pre-order traversal. But for this problem, if we put left in front of right, it's also okay. So with that done, so if nothing has returned, so we're going to return false. So that's the second treatment. But here we incorporate the set and check inside the traversal. So with that said, I guess that's the second format of solution. So we can do a check. Yeah, it passes one example. Now let's look at generic case. Yeah, it passes all the cases. I guess for this problem, it's just for a practice. So we present two methods. So one is based on Inorder Traversal, which we used the BST property, but in a weak sense, I think, for this problem. And then we practiced the standard two-pointer trick. And in the second format, we actually do a traversal of the binary tree without taking into consideration of the BST property. And then the check is for using set abstract data type and do the check. So with that said, I guess that's it for this video. Thank you.